welcome you all tonight for our discussion of the Spitzer Space Telescope. We're going to talk about infrared astronomy. A little different twist than we usually do. Hope to broaden your horizons a little bit. As usual, I'll go somewhere between 60 and 90 minutes. If you need to leave after that, we understand, but I'll ask you to try to hold your questions until then, and then we can do question and answer on the presentation and any other questions that you might have. Okay? So the Spitzer Space Telescope has been quite a productive instrument for a number of years now, as you'll see. You're probably all far more familiar with the Hubble Space Telescope, right? We've heard about that so many times. It's also been a wonderful machine. But tonight I want to acquaint you with Spitzer. Okay, so let's take a first look at the gentleman whom it's named after. Here is Lyman Spitzer, a famous astronomer from early in the mid-20th century. He was quite a powerful force in many areas, but one in particular was space telescopes in general. He played a large role in helping to promote and develop the Hubble Space Telescope, and as a result of his work, NASA chose to name the infrared observatory after him. As we'll see, Spitzer, Hubble, a number of other telescopes are part of a larger group, a larger set, I guess, of telescopes to allow astronomers to view the universe in many different types of light. So we're going to touch a little bit on that very briefly just to make sure everybody's on the same page there. You and I, of course, see invisible light. We're used to certain wavelengths of light, but as you probably know, astronomers can view the universe in many different wavelengths to learn so much more about the objects that we want to learn about. Okay, so here you see several of NASA's great observatories. At top left is Spitzer, which views in the infrared. Bottom left, Hubble, invisible light. You might have also heard of the Chandra X-ray Observatory and the Compton Gamma Ray Observatory. So NASA has made it a point to put telescopes into space to be able to see these various wavelengths. We'll talk about the reason why in just a minute here. But these allow astronomers, again, to be able to view the universe, to view specific objects in many different types of light and learn so much more about them than they might with only one particular type of light. Okay, so that's really the strategy, so to speak, of having a space telescope focused on various wavelengths. Spitzer's been in space quite some time now, since 2003. Quite a long, quite a productive, quite a very successful mission. And like Hubble, continues to be used to this day. Okay, so let's talk a little bit about some of these different wavelengths. Why do we need all these telescopes at different wavelengths? Well, the short answer is because of Earth's atmosphere. It protects us from various wavelengths of light that would be very harmful to us, but on the other hand, we're very interested in observing those wavelengths with our telescopes to, again, learn about astronomical objects. So as you kind of see here, visible light penetrates from space to the ground. You and I can go outside at night and look at the stars, of course, with our eyes. Radio wavelengths penetrate to the ground. So astronomers have long since built huge radio dishes. You've probably seen pictures of those. And those can be placed on the ground and observe the heavens just fine. A little bit of infrared light reaches the ground, not much. And one of the reasons it doesn't is because of water vapor in the Earth's atmosphere. So you might think, well, and you'd be correct, if we could get above some of the water vapor, maybe we'd see a little bit more of the infrared wavelengths. You see a little airplane there. NASA is now on its second airplane-based telescope for infrared astronomy. Okay, the current one called SOFIA. So the point is, those wavelengths reach the ground. All the other wavelengths do not. They're blocked, they're absorbed by Earth's atmosphere. So really, no ultraviolet wavelengths, no X-ray, no gamma ray reach the ground. And many, if not most, infrared wavelengths do not reach the ground. So how would you observe them as an astronomer? Well, as we have already said, you need to put your telescope into space. It's quite expensive, but there's just no getting around it. There's no getting around it. Now we're going to focus more tonight again on that infrared region. You see Spitzer there as one of the telescopes shown right here. Okay. Over here we have a microwave telescope, the WMAP telescope, Hubble invisible light, again Chandra and X-ray, and Compton integral in gamma rays. Okay? So again, what we're going to see is infrared light. Your eyes would not necessarily see it, but on the other hand, it's very real. It's definitely there. Spitzer, as we're going to see, has instruments that will detect those wavelengths. And then we take those wavelengths and we assign colors to them that you and I can see, as we'll talk about here in just a second. Okay? Here's some kind of fun pictures. First of all, let's start on the right with one of my favorite astronomers, William Herschel. Way back in the late 18th century, was doing an experiment. He was thinking about light, and he wanted to see if all the different colors of light were equal in energy. So at that time, of course, he didn't have a lot of technology. What he did was he took a thermometer and just placed it into each color of light. Kind of an ingenious way to do that. And he found that as the thermometer moved from the blue towards the red, it got slightly warmer. But here's where the real breakthrough came. As he moved the thermometer past red, the thermometer continued to get warmer. And so Herschel correctly discovered that there was light that was invisible to his eyes that could be delivering energy to the thermometer, and thus the discovery of infrared light. These days, we have sophisticated technologies you kind of see on the extreme left and lower left that can, again, look at objects in infrared light and, again, take those measurements of intensity of light and change them into a color that you and I can see. Now, we could pick pretty much any colors we might want. So as you see in those pictures there, different colors indicate different temperatures. Okay? White indicates the highest temperature, then red kind of a medium temperature, and then blue a cooler temperature. So again, in looking at these particular pictures, this is a picture of a person obviously holding a match. This is a geyser, I believe, in Yellowstone, I want to say. White indicates the hottest water, then the purple and reddish, then the yellow, then the green. The blue would be the coolest. So as we go through a lot of our images tonight from Spitzer, think in those terms that this is actually light, but what our instrument is measuring is the energy of the light, which correlates to the temperature of the object. Okay? So think in those terms. You wouldn't be able to necessarily see those specific wavelengths, but it indicates the energy and temperature of the objects. Okay, so that gives us, I think, a nice, hopeful review or overview of infrared light. Now, I want to show you a short video here from Dr. Thaler. I had the pleasure to meet and work with her at a conference one time. She worked for many years as you see, the manager of Spitzer's outreach, and so she put together a nice little video talking about infrared. I sure hope it works. No. It works every time I try it until I come up here. So let's watch and see if we can hear.
These days we're all familiar with night vision cameras, but how do these things work? How is it that you can just turn on this camera and see the invisible? Another use of night vision cameras that you might not be familiar with is their ability to see through smoke and dust. Fire departments commonly use cameras like these to find people trapped in smoky rooms or to pinpoint the exact location of forest fires through clouds of smoke. So how do these things actually work? What are we really seeing when we look inside a night vision camera? Well, it may surprise you to learn that everything in the universe emits some kind of light. It's just not the kind of light we're used to thinking about. The sun, for example, our star, emits visible light. That's why our eyes evolved to detect that kind of light. But that's not the whole story. I'm sure you're familiar with all the different kinds of visible light, all the colors from violet to red. But there are actually lots of other kinds of light that our eyes aren't sensitive to. The reason all the colors of light are different is that they have different energies. And what you see here is that the light has different wavelengths. The blue light, for example, has a higher energy, so it has a shorter wavelength. The red light, on the other hand, has less energy, so it has a longer wavelength. But that's just the light we can see with our eyes. That's not all there is. The shortest wavelength light are gamma rays, which can have wavelengths smaller than an atom. The longest wavelengths are radio waves, which can have wavelengths larger than the entire Earth. The kind of light an object emits depends on its temperature. We're used to thinking of something hot giving off light. But it might surprise you to learn that objects that are cooler, like myself, give off a kind of light too, and that's what a night vision camera can pick up. That sort of light is called infrared light. world sure looks a lot different in infrared light. Remember that what you're actually seeing is temperature. So something that's warm is going to look bright in the infrared. And something that's cold looks dark. Ice cream. Blow dryer. And infrared radiation is actually a measurement of temperature. Places on my face that are cold, like my nose, appear dark in an infrared camera because they're giving off less infrared radiation. And places that are warm, like my mouth or the hair next to my head, are brighter because they're warmer. You can even see my breath in my nose if you look carefully. And this is an ice cube. And humans, of course, are not the only things that emit infrared light. What do you think you can learn about animals by observing them in the infrared? What about reptiles? Remember, they're cold-blooded. Giraffes. Here's a Nubian ibex. What do you think horns look like in the infrared? Can you even see a gorilla in this picture? If you look carefully, you'll notice you can still see the zebra's stripes even in the infrared. How about elephants? What about a polar bear? How about a rhinoceros? Check out the horns. A cat. Notice the infrared footprints. Deer in the dark. A helicopter. Notice the plume of heat from the engine. Earth movers with hot smokestacks. A car engine turning on and heating up. Infrared light also has a lot of really interesting properties that visible light doesn't have. For example, it can often pass through things that block visible light entirely. I have a black plastic bag, and as you'll notice, you can't see through it at all. But with an infrared camera, there's no problem. But just like infrared light can penetrate some things that stop visible light, it also gets stopped by some things that let visible light through. For example, here's a piece of glass. And as you can see, none of the infrared gets through at all. If you haven't guessed, that's how the greenhouse effect works. Infrared light can't get through gases like water vapor in our atmosphere, which means that the heat is trapped and our planet is getting warmer. So what am I, an astronomer, doing with an infrared camera? Well, if everyday objects look different through an infrared camera, you can bet objects in space do too. For example, here's an image of the constellation Orion, which you're probably familiar with from the night sky. But now, let's look at it through an infrared camera. Look how much you're missing. Astronomers are also hoping to use infrared light to find planets around other stars. Planets don't give off any visible light of their own, making them nearly impossible to see close to a bright star. But in the infrared, planets give off their own light, making them much easier to find. Astronomers will soon be able to use very sensitive infrared cameras on a new space telescope, the Space Infrared Telescope Facility. And it should give us a whole new perspective on the universe. At that point, we'll finally be getting a more complete view of the universe. Right now, we don't even know what we're going to discover. There are so many wonders out there. We'll finally be able to see more than our eyes can see.
But hopefully they give you a nice view of, again, what you can see in infrared, far more than your eyes would see. And yet, especially a few of those images already of the sky showed you how different the sky may look. And that allows astronomers to interpret those differences and understand what we're seeing. So one more time, let's take one last look here at the differences. You heard her talk about different temperatures. And again, that's an easy way for you and I to kind of think about infrared light. Okay. Interestingly, we can not only get a relative idea of temperature changes, but we can get a nice idea of the actual temperature of an object in space by using a simple equation. Now, some of you may not be all that comfortable with math, that's okay. But for those that are, you notice, I'll describe briefly what we're doing here, is we take the light from an object and we'll break it into a rainbow, or what we call a spectrum, and we'll look carefully to see where is the peak or highest level of intensity of the light. And you notice in our example here, it appears to be approximately kind of in the orange type of light. In other words, there's a little higher intensity of orange light than there is blue light. Well, if astronomers measure that precise wavelength and say, look, it's a certain wavelength that is the peak wavelength or maximum wavelength, we can take that number and put it in the denominator of that equation and get the actual temperature. So we can tell you how hot the surface of the sun is. We can tell you what the temperature of the surface of Mars, or the clouds of Neptune, or a new young star being formed, whatever it might be. So that allows them to quantify their research and get a much better idea of what the temperature of different objects are. So here you see two pictures illustrating that difference. If we took a picture in visible light at the top, we might see the sun and different planets, but in the bottom, we might see them very differently in infrared light. So once again, just trying to set ourselves and calibrate our minds to understand the difference here with infrared light is that different colors indicate different temperatures. Now, during its design phase, of course, Spitzer was optimized by various astronomers for certain temperature ranges. In other words, extremely hot objects would not give off so much infrared light. They would give off other types of light. For example, ultraviolet light. Extremely cool objects would give off a very different type of light, such as radio light. But the point being that Spitzer was designed to find temperatures in a certain range, as you can see here, from about 25 degrees Kelvin to about 1,000 degrees Kelvin. Now, the Kelvin scale is very similar to the centigrade scale that you and I might be used to, or the Celsius scale, but the 0 point has moved a little bit. So it's just basically the same temperature range, moved a little bit. Doesn't really make a big difference to astronomers when we're talking about thousands and thousands of degrees to move the 0 point just a bit. But that's the type of temperatures that we're going to be talking about here with Spitzer. As we'll see, Spitzer being in space, of course, is very, very cold. The telescope itself had to be optimized, because if the telescope was giving off heat, well, that would basically swamp the detectors. It would be like trying to take a picture of a very faint object in a very bright room. It just wouldn't work very well. So I'm going to talk a little bit more about the telescope here in just a second. But the point being, as you can see, these are kind of the temperatures that we'll be talking about that Spitzer is optimized for. So here is the telescope itself, kind of a cutaway view on the left. Spitzer is not all that big, as you see in the center picture. It would fit right up here very nicely. So it's not nearly as large as Hubble, but again, optimized for various types of work. Okay, so up at the top, you see the actual telescope assembly up here, labeled number 1. Okay, you can get a nice idea of the size here compared to the technicians working on it. The mirror itself is not all that big, relatively speaking, for astronomical telescopes. Then we have a chamber here where most of the instruments are, right beneath the bottom of the telescope where the light is delivered. And we're going to talk primarily about these 3 different instruments. Okay? Finally, in the bottom, number 3, is a helium coolant tank. Why would we need helium? Well, again, those instruments are extraordinarily sensitive, and they need to be cooled if they're going to detect very faint types of light as heat. So you want to cool your cameras down so there's no extra heat in the cameras that would swamp the pictures that you're trying to take. Okay? And then finally, the outer assembly, as you see on the right. So a fairly, I don't want to say simple telescope, but a very straightforward design of a telescope, the detectors, and some coolant. You can imagine, of course, the coolant would not last forever, would it? At some point, it would run out, and that would compromise some of Spitzer's usefulness, but not all. So let's talk about these 3 instruments. The IRAC instrument images at certain specific wavelengths. Don't worry, it won't be on the test. You don't have to memorize these numbers. But as you can see, it's 3.6, 4.5, 5.8, and 8 microns. Okay, what does that mean? That means that the objects it's looking at, as you see here, would be from approximately 900 degrees Kelvin down to 350 degrees Kelvin. Okay, great. So it's going to take pictures at those wavelengths. Now we also have two other instruments, okay? And this IRS instrument, as you see, it mentions spectroscopy. What's spectroscopy? Well, that is not so much taking pretty pictures as, again, breaking the light into that spectrum so that scientists can analyze other elements of the object rather than its shape and its size and its appearance. We want to be able to determine composition. We want to be able to determine temperature, so we take the light and we break it into the spectrum. So that's its job. And as you can see, that would be at wavelengths from 5 to 40 microns. Now the MIPS instrument was somewhat of a combination instrument, did some imaging and did some spectroscopy as well, and these are at longer infrared wavelengths. So one thing I do want you to remember is when the wavelengths are shorter, okay, that indicates, the shorter the wavelength means higher energy, higher temperature. The longer the wavelength, lower energy, lower temperature. So we're going to see different images. We'll say, well, this one was taken at this wavelength, or at this wavelength, or at this wavelength. And again, we get a sense of those temperatures. Okay? We mentioned the telescope is cool. Not only that, but think of even the fact that if the telescope was in orbit around Earth, Earth itself gives off quite a bit of infrared light or heat that would also degrade the performance of the telescopes. So Spitzer was put in an orbit far from Earth. It's essentially in Earth's orbit, but approximately 1 million miles away from us. Okay, so it's out here all by itself, well far away from Earth, nice and cold. You can see the infrared universe as it was designed. You can see a lot of thought went into the design. Okay? They even put a special kind of a sunshade, so to speak, to block the sunlight. You don't want the sun's infrared light to be affecting you as well. All right, well, here's two of my favorite astronomy assistants. And once in a while, I just got to remind myself, okay, already, enough. You know, let's talk about some pictures, right? Remember these two guys? Okay, let's take a look at the pictures. Number one, we're going to start out here by looking at what are called extrasolar planets. Some of you have heard me talk about those. It's an exciting time in astronomy that we have found and are now researching planets around other stars. But let's start out with some of the early work that Spitzer did. What do you see here? They look kind of like fuzzy stars, right? What we're seeing is disks of material, primarily dust, around stars. Why are we interested in dust? Because that's what planets form from. Little particles begin to stick together, and as they stick together, they get a little bigger, and a little bigger, and a little bigger, and they gradually grow and grow and grow. As soon as they get to much larger size, of course, they begin to acquire more gravity. They can pull in more particles, continue to grow into planets. Okay, so it'd be nice to understand the stages of formation of a planet, and we'd like to understand those early stages. So Spitzer here is looking at a particular star with this dust disk around it. Well, of course, that tells us that it hasn't necessarily formed planets yet, meaning that it would be the early stages, wouldn't it? And so this has given astronomers a look at the different early stages. So dust absorbs visible light, as it says here. I've made a few notes to help us along. It also absorbs ultraviolet light, but as it absorbs that light, once again, think of it as absorbing energy. And you know what happens when you stand outside on a day like today and you absorb sunlight? What happens to your temperature? Goes up. So the dust warms up. Well, it turns out as the dust begins to warm up, we said a few minutes ago, every object at a certain temperature is going to give off a certain type of light. The dust begins to give off infrared light. And so this is a perfect place to aim Spitzer. So once again, the dust absorbs the visible light, and we say re-radiates it in infrared wavelengths. We can take a look at it and measure its temperature, measure its extent. Okay? In this particular case, you can see images taken at different wavelengths. Okay? At upper, let's see, we've got here 24 microns is at upper left, up in the green here. So this is a little bit warmer dust up here, 120 degrees K. Okay, 70 micron at lower left. We said longer wavelength, a little bit lower temperature. And notice it's not perfectly symmetrical, is it? So this is telling us something about the formation. Why is there a little bit more dust in one region or another? We don't know that exactly. That opens the door for us to begin to possibly think about some ideas, hypothesize, we would say. Say, well, maybe this happened, or maybe that happened, or whatever the case may be. So even though these are somewhat fuzzy images, I think you get the sense that it at least is a very good first step at looking at the early stages of planet formation. To give you some scale here, you can see I put the number in there, 370 AU in diameter. What's an AU? Probably a lot of you know. Astronomical unit, that's the Earth-Sun distance. So the diameter of this disk is 370 times the distance from Earth to the Sun. That's a pretty big disk, isn't it? Our solar system is more like maybe half that diameter when you consider that it also has some particles in the outer regions. Okay, so again, a fairly typical solar system. This would be a younger solar system. Our solar system would not have this much dust. It would have a little, but not this much. Okay, so an early look here at planetary formation by Spitzer. Now again, I mentioned we can get planet temperatures. Here's one example of what Spitzer's done more recently. Okay, and it does give us the temperature distribution on a particular planet. How do we do that? Well, I won't be able to go into great detail tonight, but you may recall from some of my other lectures that occasionally we might be fortunate enough that a planet will literally orbit around its star and pass in front of the star from our perspective and block a little bit of its light. It's a very small amount, but it's measurable, and it gives us an idea of, well, how big is the planet, how fast is it moving, you know, those type of things. And if we're smart enough, astronomers can measure that carefully, and they can kind of untangle most of the starlight from the planet's light itself and get a pretty good idea of the size of the planet and the temperature of the planet. In other words, if you can isolate the planet's light, like I said once again earlier, you can determine its temperature. Okay, so here's a real, again, exciting kind of next step, so to speak. Spitzer doesn't necessarily see the planet, but it is able to see the difference as it passes in front of or behind the star. And if we subtract out the star's light, then we're left with just the planet's light, aren't we? And we can start to say some things about the planet's size and temperature and so forth. Okay, so real exciting things. Sometimes the images themselves are not super dramatic in the sense that really all we're really doing here is measuring the intensity of the light. We're measuring the intensity of light from the star, and when it dims a little bit, we say, well, wait a minute, there's the planet. When it goes back to normal, we say, well, the planet's not visible anymore. So again, we can subtract out the star's light and learn about the planet. Okay? Let's move on a bit and look out into different regions in space. We notice clouds of dust. And notice the difference now, as we've talked about several times, between visible light, what we'd call near infrared or shorter wavelength infrared, and mid-infrared or a little bit longer. It looks different, doesn't it? In other words, if you look on our left picture in visible light, this is what you and I would see. We'd say, well, you know, we got some pretty red gas here. We must have some dust because look at this little kind of finger of dark dust is blocking the light behind it, isn't it? Well, if it's dust, we said it would normally absorb some starlight and re-radiate it in infrared. So you do see a little bit of the dust here, don't you? If you look carefully here. Also, in visible light, we don't see much of the dust and gas near the star. We do see a little bit of visible light reflected by the dust and gas. But in infrared, again, the dust and gas absorbs the light, and then it re-radiates it in infrared light. And so notice how the center region here gets brighter and brighter as we go to longer wavelengths. In other words, here the dust is warm enough to give off this very subtle, very faint infrared light that Spitzer can see. So again, these are two or actually three different ways, of course, to look at the same region in space and tell us about the dust. Astronomers can go further. They can get more specific and tell you the size of the dust particles, the density, those types of things, even its composition sometimes, by carefully studying images like this. So again, you really see how Spitzer, as we keep saying, gives us a very different view of the universe, doesn't it? Here by looking at infrared wavelengths, at a region that only can be seen, you and I, in visible light. Here's an even more dramatic example of that. Here's a dust cloud out in space, okay? And in the lower left, the dust looks dark because we're looking at visible light. So in other words, it's in the foreground, so to speak, and it's blocking some of the light in the distance, but the larger image, again, shows us the dust has absorbed the light, and you probably heard me say this several times now, re-radiates it in infrared, doesn't it? So it's two different ways to look at the same region in space. And once again, astronomers can get more specific, tell you about dust particle size, density, extent, composition, all different types of things by looking at the two pictures. Okay, so again, you start to see, I think, the capability of Spitzer here. It's a little different than a typical telescope you and I might look through, but it's telling astronomers so much more about what we're seeing there. So it's really opening wider our view, our understanding of the universe. Here's a real remarkable discovery. On the left, you see artist's impression of our sun and our planets. In the lower right, you see something called a brown dwarf. What's a brown dwarf? Well, think of a brown dwarf as kind of a failed star. What do I mean by failed? Well, it's not truly a star because we define a star as an object that's hot enough inside to generate huge amounts of energy. Some of you are well familiar with this. Nuclear fusion occurs in the center of a star, and our sun gives off an awful lot of light, an awful lot of energy. Well, a brown dwarf star is not massive enough, it's not big enough, doesn't have enough material, doesn't have enough gravity to squeeze itself down and get hot enough inside to do this. So essentially, it's just sort of warm. It's just sort of warm. And if you look closely, the scale here is pretty accurate. A brown dwarf can be roughly the size of the planet Jupiter. So clearly it's much smaller, but the key for astronomers is it's much lower mass. It doesn't have enough gravity. It doesn't generate nearly as much light. Well, if it's not going to generate a lot of light, in other words, it's not hot enough, you see where I'm going? If it's not hot enough to give off visible light, what type of light do you think it might give off? Yeah, infrared light, exactly. It's a cooler object, and as a result, going to primarily give off infrared light. Well, again, you know where I'm going. This is the ideal object for Spitzer to study. Okay, so a brown dwarf would give off very little visible light, but it would give off a significant amount of infrared light. Somewhere in the range of 1,000 degrees or so is its temperature, anywhere maybe from 500 up to maybe 2,000. But the point is that is right where Spitzer's optimized for. Okay, so let's take a little closer look at some of the results. Now, we can't clearly see something so obvious as you're seeing here. This is an artist's impression, but this kind of dry, boring graph tells astronomers a lot. What's it really telling us? Well, you can see, first of all, the measurements of Spitzer are shown as dots here. Okay, so what were we looking at? We're looking at the brightness or the intensity, the amount of light, and we're looking at it at different wavelengths. So Spitzer says, well, at this wavelength I measured this much light, and at this wavelength I measured this much, and so on and so forth. Okay, so clearly the object's giving off a little bit more light down here at these shorter wavelengths, a little bit less here. These are the actual measurements. Okay, so how do we interpret that? Well, astronomers can build basically a model of a brown dwarf and say, look, a brown dwarf, if it's this big, if it's this massive, should be this temperature, and it should give off light, as you see, this red dashed line. Its light should kind of decline over here on the right. Well, clearly, Spitzer's measurements show that this particular brown dwarf, that did not decline, did it? So you say, well, how do we explain that? Well, we can easily explain that by also modeling what would a disk of dust look like around the brown dwarf. Well, a brown dwarf with a disk, again, the disk would absorb some of the light and re-radiate it at longer wavelengths. So a disk would give you light as you see in the green line. Well, the point being, if you add the green and the red lines, you get a very good match to what Spitzer observed. So you see how astronomers do this? They essentially say, look, the brown dwarf should give us this light, the disk should give us that light. If we put them together, that's what we're seeing. So wouldn't that be pretty solid evidence to say, well, the star probably has a disk around it, doesn't it? Okay? So this is a real nice example of, again, what Spitzer can do for us. We might not be able to necessarily take a picture of that disk just yet, but Spitzer can tell us there has to be a disk there. And once again, that adds to our knowledge of how that brown dwarf formed and lives and changes and all these things. But that's a very important part of understanding brown dwarfs. Okay? So again, one of Spitzer's results there is the measurement at different wavelengths of the intensity. Let's move on and talk about how else Spitzer can help us understand stellar birth. I've got a lot of notes kind of jotted down here for us. Got a beautiful region here, don't we? Looks like something you want to put on your desktop computer. Okay. What's going on? Well, it is a region where stars are forming. And I can only go into so much detail, but essentially you say, wow, there's a lot of bright stars, a lot of pretty colors. Now again, we have added those colors and exaggerated them a little bit to indicate different wavelengths of light in the infrared. Okay? Up towards the upper left, down towards the lower right, you see these different colors. Okay? And essentially, again, a lot of young stars here. There's another whole story to that. But the point being, Spitzer, again, fills in our knowledge of these young stars. The dust that you're seeing, Spitzer's able to see through. The infrared wavelengths can get through the dust, whereas the visible wavelengths could not. I didn't get a picture here of this object in visible light, but essentially you'd see a fairly dark region. The dust would not allow visible light through. Okay? Interestingly, too, not to go into a lot of detail, but astronomers can also model how they think stars should form, some of their features, some of their characteristics. Well, we should maybe see it do this or see it do that. And one of the things that can be very typical for a young star is that for a short period in its life, early on, it will literally shoot jets of material out its north and south poles. It's kind of a whole another story, but the point is, with a disk of material around it, it's not able to send out as much light in those directions, but it is able to send out more light from its north and south pole. Well, if you look closely, you see a beautiful example of that right here. Look at this disk of material, it's kind of warped. And look at in orange, Spitzer can peer in and see extra light pouring out of kind of the north and south poles, so to speak. So that's a beautiful confirmation for astronomers to say, look at that, that's exactly what our models predict, and there Spitzer has confirmed it for us. Okay? So again, a very complex region, a very complex picture. We can't go into a lot of detail, but again, the different colors are indicating different wavelengths, which indicate different temperatures of the gas and dust. And by analyzing these types of pictures, we can learn a lot about the material. Again, its temperature, its density, its composition, particle size, lots of different things here. And it adds to our knowledge of stellar formation. So a pretty picture, but full of information for us that Spitzer's able to uncover. Even more dramatic, perhaps, is this particular region. Okay? And as you can see, some of you might be familiar with the Cone Nebula. This is a dramatic view. And notice this time what we've done, or rather Spitzer's done, is given us images in 3 different instruments. Do you see that? The upper right is the IRAC camera, the MIPS camera on the lower right, and then a combination. Okay, so what's going on here? Well, again, it's pretty obvious, very dense, thick dust. This is where stars form. And as you look through the image, you see quite a few little beautiful little pink little dots of light. These are very young stars. Much of their light is reddened because much of their light is passing through dust. The dust tends to block the blue light, but it will let the red light through. So we're kind of seeing almost like a filtering effect, so to speak. Okay? And by examining these objects closely, astronomers have been able to pin this down, that star formation is occurring right now. Now, some of you are a little more familiar than others, maybe. It does take time. It can take millions of years, but this is a region where star formation has really kind of just begun. This is probably less than 1 million years old. In fact, possibly as low as 100,000 years old. For astronomers, that's very little time, 100,000 years, okay? So these very young objects are still contracting under the force of gravity. They're getting hotter. But before they get hot enough to become a real star and give a burst of light like our sun, what do you suppose happens if they're not hot enough? What kind of light are they giving off? Yeah, infrared light. So once again, perfect place to aim Spitzer. That's what its job is, isn't it? To take a look in here and show us what are the temperatures of the gas, what's the density, what's the composition. Okay, some regions are going to be cooler than others or warmer than others. And again, it allows astronomers to go in there and see what's really happening. They can make their models, but sooner or later you want to go out and you want to compare your model to what's really happening out there. And again, a beautiful view here from Spitzer to show that. You notice, of course, again, before we move on, in the very center is a fairly dense cluster of stars. Stars don't form one at a time. They form in large groups. And here Spitzer is able to look through a lot of the dust and show us a cluster of young stars. Okay, so what a dramatic view there. Well, let's move on. After we talked about stellar birth, sooner or later, there's stellar death. Anybody recognize this object? I bet a few of you do. You can see the name there, yeah, the famous Ring Nebula. Probably looks a little different than you remember it. Why? Well, you and I typically see this bright central region in visible light. But notice how much more there is to it when Spitzer takes a look. Why is that? Well, simply put, there's dust outside the main bright region. And as a result, the dust again absorbs light and re-radiates it in longer wavelengths. Excuse me. This gives us a much, again, broader view of the object, doesn't it? It allows us to see that this object is not this big, but much bigger. How could it be bigger? Well, it gave off this dust earlier in its life. So at some point, the star gives off some dust, excuse me, and then later on, the light lights it up. So this really, again, extends our understanding of the star's life cycle. At some point, the star expelled the dust first, and then later on, gave off more gas. So again, a dramatic view here of a familiar object. Let's see. I think that's what I wanted to explain there. How about this dramatic view? The Helix Nebula. Once again, a similar object. A star has expelled its outer layers. And here, Spitzer is able to show us in great detail the different regions. Note the color difference. Here, Spitzer's taken images at different wavelengths and composited them together. See some red, some orange, yellow, green. Well, the point being that there's slightly different temperatures here because of the slightly different wavelengths. So it makes sense when you say the center would probably be a little bit warmer, wouldn't it? The outer regions would be a little bit cooler the farther they are from the star. And so as a result, Spitzer is able to, again, give us that detail and show us the different regions of this particular object. And tell us, again, a little bit about the composition, the density, and those kind of things we keep saying of the particular regions in this object. So, again, having different wavelengths in the different cameras allows Spitzer to do this for us. When you compare the two, this Helix Nebula is a little bit closer to Earth than this Ring Nebula, but we see some similarities, but some differences, don't we? So these particular objects, called planetary nebula, can have dramatic differences. Their sizes, their shapes, their ages, their densities, their temperatures, their composition, all these things. And it's just like studying people, I always say. They're always different, aren't they? Spitzer allows us to compare and contrast them. Let's move on now and talk about the Milky Way galaxy. Here's some different views on the right. At the top, we have red visible light. If you were to go out to a really dark spot somewhere out in the middle of the desert or somewhere and get a really, really good view of the Milky Way, you'd see something very similar. You'd see obviously some brighter regions, but you'd also see some darker regions. Why? Because this is where dust is throughout our Milky Way galaxy. Of course, we're inside the Milky Way, so we're trying to look out at the stars in the distance, but there's dust in the way and it's blocking the light in visible wavelengths. Well, we've said several times now, haven't we? Spitzer has the ability to look through the dust, doesn't it? So notice in our middle and bottom images, Spitzer does exactly that. It's able to look through the dust and show us how many more stars, how much brighter the Milky Way galaxy is and towards the center at the shorter infrared and longer infrared wavelengths. Why is the brightness kind of in this horizontal band or plane? Well, again, you probably know the Milky Way is a flattened plane, so here we are inside of it, and picture what you would see is, again, the band of the Milky Way's light all the way around you. If we're inside of a disk, what we've done here is, of course, just taken that wraparound view, so to speak, and just flattened it into a flat picture. So one edge of the picture matches the other edge of the picture. You could pretty much wrap it around your head. But again, just very simply, these three images show us clearly how Spitzer can look through the dust, show us things that we can't see in visible light. You might know that we can't really see the center of the Milky Way in visible light. It's blocked in visible light. But in infrared light, we can see it much more clearly. So again, a very dramatic example of how Spitzer allows us to look through the dust and see so much more. By doing that, Spitzer's enabled us to make this recent map of the Milky Way. This is where you live. Okay, beautiful, beautiful spiral galaxy. We have this elongated yellow central bulge region. We have also the beautiful bluish disk. And that disk, of course, is lit up by these spectacular spiral arms. Now, oftentimes you see kind of a model Milky Way. If you read an astronomy book, you say, oh, the Milky Way is a spiral galaxy. But this is more specific. This is the actual structure of the Milky Way. Spitzer did some survey work years ago, and by looking at that survey, when we use that term, they were able to piece together the locations of millions of stars, get their distances, and really actually give us a true picture of the Milky Way. So yes, this is an artist's impression, but it's a very accurate impression. So what did we find? Well, as you can see, there's kind of two major arms coming out, one here and one here. There's a few other minor arms. Interestingly, as I noted in my notes here, the major arms are star-rich. In other words, lots of stars, obviously, but the minor arms are gas-rich. So what? Well, what that means is there's a lot of raw material to make new stars. So right now, the bright arms, the two major arms, are all lit up. They've formed a lot of stars, but come back in a few 100 million years, and we might see other regions lit up far more with young, bright stars. Okay. So again, this is an artist's impression, but it's going to keep saying a very accurate impression and a very accurate map of our Milky Way. This is a very remarkable map, being that we're inside of it. Be a little bit like me saying, well, I want you to map out this building by staying in this room. That'd be a little tricky, wouldn't it? But Spitzer allows us to look through the dust that's in the way, almost like you could look through these walls and measure different parts of the building. Spitzer lets us do something very similar by looking through the dust. How about other galaxies? Well, they're equally spectacular. Maybe you've seen pictures of this particular one called M81. On the left, a beautiful view in visible light, but look at what Spitzer sees in infrared. Now, why have we colored it as we do? Because, again, we keep saying the different wavelengths. But notice our central region is very bright, but now look at our spiral arms. My goodness, what a beautiful contrast, all these regions out here. What's going on? Well, that bluish region on the right indicates to astronomers that there's not so much dust and gas there, but rather older stars there. The center of the galaxy is fairly old stars. They've pretty well run through much of their life, but not so in the spiral arms. The spiral arms, instead, are very bright, vigorous regions of young stars that are very, very bright and energetic, kind of like people. And they're lighting up the spiral arms. Okay, so you just see a very dramatic difference here. Yeah, you can kind of make that out in the left-hand visible image, but boy, isn't it even more dramatic in the right-hand image? This allows astronomers now, if they're studying star formation, We saw earlier some kind of close-up views, didn't we, where you'd zoom in and look at this cloud or this cloud or this cloud. But see, here we're stepping back and we're getting a big picture of a spiral galaxy, and we're saying, where are those regions? This helps us not only understand star formation, but some astronomers could take this information and they could start to talk more about the galaxy itself. Why does the galaxy have these beautiful spiral arms? Well, the first thing you got to do is map them, don't you? And that's what Spitzer's doing. So it's mapping out the regions of star formation. Astronomers then go back and try to model that. Say, can we duplicate that? Can we simulate that? Then we'll have a better understanding of how a spiral galaxy forms stars only in its spiral arms. Okay, so again, a very beautiful, yet very informative view from Spitzer here. We see something similar in other galaxies. These, again, are not colors your eye would see. These have been kind of color-coded, so to speak, to indicate various wavelengths. But here you see the beautiful blue disk now is highlighted with this very vivid kind of pinkish region. Those pinkish regions, once again, are indicating certain wavelengths of light, certain temperatures of light that indicate star formation. There's dust there in those regions, and young stars are warming up the dust, and Spitzer's able to see the dust glowing brightly, and you'd say, wow, that's right where the star formation is going on in those particular regions. So again, whether it's a single galaxy or multiple ones, astronomers could look at that and get a much better idea, test their ideas on where star formation should occur in a spiral galaxy. Yet one more view, a little different galaxy, very similar though. You see once again that blue disk in the background, these reddish pinkish regions lighting up the foreground, really indicating to us where the star formation is. And you know, on these particular images, we take for granted what a beautiful picture and the beautiful spiral, but you've got to remember that these are enormous objects. You probably know that galaxies are enormous, and by that I mean tens of thousands, if not hundreds of thousands of light years across. And how big is a light year? A lot of you know it's about 6 trillion miles. So these are big. And these are enormous structures that we have to step back and try to understand. How do you form this? How does it maintain that? All those kind of questions keep astronomers very busy. I like to say it keeps them up at night. I know that's pretty bad, but you know. All right, one more view here. A little different object. Probably many of you are familiar with the galaxy M104. And what a dramatic view. Several times now we've said, well, this bluish region has been color-coded to tell us it's a slightly different wavelength, slightly different temperature, right? These are older stars. Notice here a very clear spherical distribution, right? Kind of a gigantic sphere of stars, and yet obviously the very dramatic disk. Okay? What really struck me when I first saw this picture some years back was not just that we could see clearly the front near edge of the disk, but that we could see all the way around. In other words, we're looking through the galaxy. This was a very remarkable, almost unprecedented thing when Spitzer released this image. In other words, it's so good at looking through the dust, it literally looked through the galaxy to the back side of it and found the disk all the way around the back. Okay, so a little different version. Here, of course, we're looking at the disk pretty much from the side, from the edge, so to speak. Whereas here we're looking down from above, aren't we? Here we're looking down from above the disk. Here we're looking from the edge, but you get the same idea. Again, very dense regions of dust and gas where stars are forming. So Spitzer's had this unique ability to, again, take these different wavelengths, piece them together, and give us a very clear view. This particular image, they did add some data from Hubble. If I have my notes there, yeah. And it helps us, again, get the best possible view, but Spitzer added in much data, and so, again, you use the two together in combination to get an even more dramatic image. Careful measurements tell us, as it says here, that this disk is slightly warped. It's not perfectly smooth and flat and symmetrical, and as a result, you say, well, wait a minute, why is it warped, right? Well, there could be a lot of reasons, but that's where the fun begins for astronomers, is to start possibly putting some ideas out. Well, maybe it's this, maybe it's this, maybe it's this. Let's explore those and see if we can untangle what might have happened there. So M104. How about this train wreck? Okay, you got two galaxies merging or colliding. So let's see, where should we begin? First of all, this takes quite a bit of time. These are large objects. Although they're moving fairly fast, they're very large objects. You got these two galaxies coming together, okay, over literally millions of years. It's an extraordinarily complex problem that we still can't solve. How do they interact? Well, each one has billions of stars, each star with its own gravity. They're all kind of pulling on each other. It'd be like me having a string to pull on each of you, and you each having a string to pull on everyone else in the room. And I'd say, okay, figure it out. That would take a while, wouldn't it? Well, astronomers are sometimes big-time supercomputer users for this exact reason. They want to model something like that and see if they can figure out what's going on. As these things are moving, they each may have a different mass. They may have a different shape. There may be a certain angle between them. There may be a certain velocity. All kinds of variables to take into account. And yet, once again, ultimately, at some point, you have to compare your ideas, your models, your theories against what really happens. So here's what Spitzer's doing for us. Again, false color image. Once again, that blue, smooth background. And yet, once again, that very bright, reddish, pinkish regions where we have a vivid star formation. Okay, so these two are approximately 140 million light years away. And the merger began about 40 million years ago. One of the things that Spitzer's been able to help us add to our knowledge, essentially, is that when this occurs, you have, again, these regions of dust and gas colliding together. Now, the stars themselves are fairly far apart. They rarely, if ever, collide. There's so much space between them. It'd be about like having a basketball here in Chicago and a basketball in LA. Are they going to collide? Probably not. I mean, if you had billions of them at those distances, maybe. But the point is this: the dust and gas clouds are much bigger. They can be light years across. So they're much more likely to collide. So what happens when they collide? Well, when the dust and the gas clouds collide, their density increases. Essentially, they do affect each other. And when the density increases, you can imagine their gravity increases, wouldn't it? If you have a very thin, faint, diffuse cloud, well, there's probably not so much gravity there. But if you have a very dense cloud, there's just plain more gravity there, right? So the point being, the higher the density, the higher the gravity. Gravity is really the key, we said earlier, to star formation. When the galaxies collide, the regions here of higher density are where star formation is triggered. Star formation is triggered. We get a burst of star formation, so to speak. And that's, again, exactly what Spitzer is showing us here. So even though it's only a snapshot in time, it does give us a really good understanding of exactly that. One snapshot in time of two galaxies merging. You can come in here and astronomers can measure this. You can probably see by eye that this galaxy looks greatly distorted. This arm looks reasonably normal, but where does it go here? There's a great distortion right here. Okay, and this spiral arm is disrupted dramatically. So again, the galaxies are greatly disrupted, but this is a beautiful example of Spitzer giving us details on the galaxy formation. I know I'm going fast, but there's so much to tell you. Now let's look even deeper into the universe. Okay? Typically, we might think, well, we need Hubble Space Telescope for that. That might be true, but Spitzer can play its role. This is what we call the Hubble Ultra Deep Field on the left. This is one of the most distant views of the universe that Hubble gave us. And you can see a little blue box down here that they've isolated. What's going on? So Hubble takes pictures primarily in visible light. It can go just a little bit into the infrared. Okay? So here's a close-up view again of that region. And you see a nice, beautiful spiral, but they got this blank area circled. Why is that? Because in visible light, you don't see much. But in infrared light, you do. Okay, so here's a Hubble picture in what we call the near infrared or shorter infrared. It's just kind of barely past visible, barely into the infrared. Hubble did pick up a little smudge there. Well, we'd like to know a little more about the smudge, wouldn't we? So we turned Spitzer. Now, Spitzer doesn't have the size and the power of Hubble, so everything looks a little fuzzier, a little grainier, but look at what Spitzer shows us. it's farther into the infrared. And it's able to see this much better, okay? So you can see how Hubble and Spitzer can be used in a very complementary way, can't you? Okay? So what is this all about? Why is that particular little galaxy only visible in infrared? All evening I've been saying, well, you know, the dust blocks the visible light, right? And Spitzer can look through it. This is a little different situation. Everything I told you is still true, don't worry. But the point being, this is a very remarkable observation. Why? You see my notes here, okay? You might know that obviously the universe is expanding. We can measure galaxy distances, we can measure their velocities, and we can say, you know, the farther out they are, the faster they're receding from us. Okay, that's called Hubble's law. Well, when Hubble took this huge picture on the left, this ultra-deep field, it's seeing some nearby galaxies that are fairly bright, like this beauty, and that one, you know, and that one. Those are reasonably nearby, but there are some that are extraordinarily distant. I don't know, I'll just pick one out. Because pretty much everything in that picture, every little dot of light is a galaxy. Those aren't stars. And as a rough rule of thumb, the smaller and fainter the galaxy, well, the farther away it is. Makes sense, right? So here's the point. When a galaxy is at a certain distance from us, the expansion of the universe, as the galaxy is moving away from us, takes its light and it shifts it slightly. It kind of stretches out the light to a little bit longer wavelength. Now, if the galaxy's not too far from us, it's not a big effect, but the farther away the galaxy is, the greater the effect becomes. So the point is this. In the nearby galaxy here, okay, Hubble takes a picture and you say, oh, you know, its light is stretched out a little bit. Okay, great, you know. But the farther out you look, the more the light is stretched to longer and longer wavelengths. This little galaxy looks red. Its light is in the infrared. Why? Because its visible light has been stretched into infrared light. Okay, so it's not so much a matter of dust in the way this time. It's a matter that the galaxy, stars, gave off visible light like any good star does, but the light has traveled so far that the expansion of the universe has stretched it out to longer infrared wavelengths, and that's what Spitzer sees here. Okay, so this is a really dramatic example of how much the light from a galaxy changes as it travels throughout the entire universe, okay? So one last comment here on this whole idea. You say, well, wow, you know, that's really pretty crazy stuff, right? This is why the successor to Hubble is going to be optimized for infrared light. It's going to kind of be, I don't want to say a combination of Hubble and Spitzer, but the point is it's going to be bigger and better and stronger than Hubble, but it's going to be able to go off into the infrared because that's what we want to study with it. Okay? So a real dramatic image. Hopefully that made sense. That Spitzer, even though it's smaller, sees this object because the object's light has literally been stretched out into longer infrared wavelengths than when it left the galaxy. Pretty remarkable image there. So where's Spitzer today? What's it doing? Well, it's not what it used to be, but it's still chugging along. I mentioned at the beginning a tank of coolant, right? Liquid helium to cool the detectors. Well, we ran out of coolant. So we can't cool the detectors. So that means it can't use certain instruments to find the very lowest temperature objects or longest wavelengths. Okay, well, it's still a very useful tool at other wavelengths. So in other words, the very longest infrared wavelengths, you can't really observe there anymore. The instruments are out of coolant. Can't do that. But it can still observe at slightly shorter infrared wavelengths. So they call it the warm phase or the warm mission, so to speak. But it's still been very, very productive. Plenty of things to do. Plenty of things to do, as I'll touch on here, okay? Just in the final artist's illustration, Spitzer's still on the job after, boy, what's it been now, 12, 13 years, something like that? Okay, and I'm going to give you one last teaser here in just a second. I I wanted to just mention real briefly, the Europeans did follow up Spitzer with an even bigger infrared telescope called Herschel. Herschel was, well, a bigger infrared telescope. Now, you looked at a little bit different wavelengths than Spitzer, so they're complementary. Bigger telescope didn't last as long, though. Why not? Because it's working at those longer wavelengths, and it ran out of coolant. Okay? So I won't be able to have time to go off and describe all of what Herschel has found. I'll give you one picture here. Okay, it looks a lot like some of the ones we saw earlier. Herschel's looked out and found very cold, low energy, long wavelength gas and dust. Okay, and I won't read you all of this. There's a lot of information here. But the point is, very productive telescope. Helps us learn even more about some of the regions, some of the wavelengths that Spitzer could not. Okay, I want to finish. Well, I thought I had one more slide in here for you. I guess not. But in conclusion, I'll just again summarize. I think a lot of what we said is that Spitzer's been a very powerful, very productive tool for us. There is a website there if you want to go have a look at it to see what the latest is. Okay? And it continues to do fascinating work. I'll just kind of, I guess, verbally mention one more thing here in just a minute. Maybe when we take some questions, I'm going to bet somebody's going to ask me. But just one last reminder before I conclude here is that if you like this kind of stuff, which you're here tonight, a lot of you probably get my emails, and you know that I am finally got my lectures out on YouTube for you. So I always say, if you just can't get to sleep at night, this will do it. You know, this will do it. There's a whole series on the solar system. If you'd like to learn about our solar system, there's the first few there. And then there's a whole series on stars and galaxies. There's some there. So yeah, if you have trouble getting to sleep, just put one on and it'll do the trick. Those URLs that you could jot them down, I think they're on my emails as well. Okay. I hope to see you back in October. Very different topic there. We're going to talk about NASA's mission called Dawn, which explored some minor planets, Vesta and Ceres. So thanks very much for coming tonight. Hope you enjoyed that and learned a lot. Love to have any questions if you have any. Who should I pick first? How about in the back there, and then I'll come right to you. Okay, so the question was, can Spitzer identify molecular bonds? In other words, molecules in space? Yeah, that's a good question, and the answer is yes. Molecules are typically, well, they are obviously atoms joined together, and they would tend to give off certain specific wavelengths as well. And just as a general answer is yes, they've been able to say, oh, look, there's a cloud with molecular hydrogen is a very common one. I'll just use that example. Okay, 5 minutes ago? That's a very good question. You've been paying attention. So the question was, an early slide showed William Herschel looking at a spectrum of light, and it implied the blue was cooler than the red. And his comment was, well, wait a minute, blue is a shorter wavelength, higher energy. Shouldn't that be a higher temperature? And you're pretty much right on the money, except for one thing really, is that the intensity of the light is less. In other words, if I was to draw a graph, I could probably take you back actually, you'd see that, whoops, that's not going to work. I guess we could go all the way back. Way back here somewhere. Remember, Herschel was using a very simple thermometer, which is kind of a crude device to be using for this. But the point being, notice how the blue intensity is lower here and the red intensity is higher here. So even though you're exactly right, one blue photon of light has more energy, and technically you'd say, well, it has more energy and a higher, quote, temperature, there's a lot more of the red photons. So in that sense, Herschel's results weren't really what you'd call rigorous.
See, that thing comes up, not that particular picture, that concept comes up
Sure.
in physics discussions,
Sure.
and they never clarify
Okay.
that there's less blue light
Okay.
photons coming than there were red. So they put blue as cooler, and yet I'm thinking blue is hotter.
It's higher
Blue
energy.
Stars are hotter.
Yeah. Again, if you compared a blue photon to a red photon, a single particle of light, yeah, the blue one has more energy, and technically you'd say, well, technically it has a higher temperature. If I took 1 million blue photons and 1 million red photons, that would have a higher temperature. But if I got 10 million red photons and 1 million, a crude thermometer is going to say, no, there's more energy over here because of intensity. So good question. Hopefully that clarified it. Is that?
Yes.
Okay.
So it's because of the intensity?
Yes, so there's more than one factor. And I think what you want to take from that is to just say, well, again, Herschel just basically found that there was light beyond the red. It wasn't a rigorous thing he did, but he did a good job. Yeah, this number here is just, I won't say an arbitrary number, but it's a number that's based on the units that you use for wavelength. Typically, astronomers like to use nanometers, 10 to the minus 9th meter. So you say, well, if I change that to microns, then that number changes a little bit. But that's just relating the wavelength to the temperature. Nature was kind of neat, made it simple for us to say, it's real simple to get your temperature if you know the wavelength, yeah. Okay, so the question was the 2.9 times 10 to the 6, why that number? Okay, another question, man? The question was, well, in this picture, you didn't talk about the planets around a brown dwarf. I guess I'll use that as my segue into what I wanted to tell you. I'm very disappointed. I wrote 2 new slides, and I don't know where they went. Maybe they're here somewhere. Hold on. Anybody hear of TRAPPIST-1? Everybody's going, hey, yeah, I think I did actually. There it is. I should put my slides where they belong, don't you think? TRAPPIST, what's TRAPPIST-1? Okay, so TRAPPIST is a telescope. I forget what the acronym means. But the point is, we've been looking in recent years at a lot of different stars for planets, right? And they found a lot. So this particular telescope found this star, said, hey, it looks like there might be some planets. Well, astronomers right away take multiple telescopes and look at that star and say, let's see if we can find out one of those was Spitzer. Okay? So TRAPPIST-1 is a very cool dim dwarf star about the size of Jupiter, about 40 light years away. It has several planets. So they swung Spitzer over and said, let's take a look. Spitzer measures the drop in the light as the star has a planet pass in front of it. In this case, it turned out to be a very complex system. It has probably 7 planets. That's a lot. So imagine if one of them passed in front, or 2, or 3, or at different times, say, wow, that's kind of complicated. How do I figure out which is which? Well, that's what the challenge has been. Okay, so Spitzer measures those, and it's, again, quite good at this. Why? Well, in this particular case, because I said it's a very cool star. Sound familiar? We've been talking about that all night. Longer wavelengths, infrared wavelengths. So let's get Spitzer to take a look. So what did they find? Well, again, they found these planets. Now, there's a lot of excitement because you might have heard people say, hey, 3 of these planets might be in the habitable zone. Have you heard this term? What's the habitable zone? It sounds very promising, right? And I always say to my students, I'm not trying to be pessimistic, but on the other hand, I want you to be realistic about what we're finding. Be clear about what we're finding. The habitable zone means that if a planet is in the habitable zone of its star, its temperature is such that liquid water could exist there. It doesn't mean that it does exist there. It means it could exist there if there was an atmosphere. Okay, so just understand it's really a temperature thing. When you hear the word habitable, people right away start saying, hey, wait a minute, is there life there? Well, we don't know that. Okay, there might be. Who knows? Okay, so the point is this. Being a very small, cool star, you can imagine to stay warm enough for liquid water, you'd have to be pretty darn close, wouldn't you? If you were the same distance from that star as you are from the sun, we'd be frozen solid. The star doesn't give off nearly as much heat or energy or light, however you want to say it. So they find these planets. All 7 of them orbit this little star closer than Mercury orbits our sun. To give you some idea, all 7 of them. The closest one orbits in like 3 days. That's how close it is. So you say, wow, they're really close to their star. They're almost kind of huddled close to the star to stay warm, right? Okay, great. This is all very interesting. It's a new type of solar system that maybe we've not seen before. It's very different than ours. So this is cool. Okay, great. First of all, notice how big the star is compared to Jupiter. It's a very small, cool, dim star. You notice its planets here. They've just sort of shown you what we think probably their sizes are. We don't know a lot about them yet, but we're working on it. Their sizes are not too different from good old Earth. So that's exciting. Wow, we found a star with planets about like Earth, or at least the same size as Earth, I should carefully say. But they're huddled close. Hey, they could they have liquid water? Well, they have the right temperature for liquid water. Be careful with that. So a lot of people get excited, say, could there be life there? We don't know. But here's what I always like to explain to my students. There are a number of other factors before you start talking about life. Okay? One of them is what I noted here. I was making some notes yesterday. okay? The planets are so close to their star that the radiation would strip their atmospheres away in a few billion years. Now, that doesn't mean that there's no more hope or no more chance, but in general, they're so close, there's a lot of radiation that would damage an atmosphere, and we're pretty sure you need an atmosphere for life, don't you think? Now, there is one possibility that I mentioned there. If a planet like Earth, for example, has a magnetic field, it will help shield you somewhat from that, but it's no guarantee. Okay. If the planets have atmospheres, we're going to be able to see, as the planet passes in front of the star, some of the star's light is going to go through the planet's atmosphere, and it's going to affect the light. So in other words, we take a picture of the star when there's no planets in front of it and say, well, this is the star, right? And then we could take a picture when maybe one planet passes in front and say, aha, wait a minute, it changed a little bit, and that little change is telling us something about the planet if it indeed has an atmosphere. So that's currently kind of what they're working on right now is, do they have atmospheres? We're looking to see. Okay. So my point is, yeah, it's a very interesting system. Spitzer's been part of the fun. It's given us a lot of good data. It's confirmed that there are these planets and they're orbiting like this and da-da-da. But you ought to be a little careful, cautious about jumping and saying, well, they're the right temperature, maybe there's life there. Well, maybe I'll win the lottery tomorrow too, you know. I don't know. So, fascinating system. Once again, you can imagine if Spitzer's doing exciting work in infrared, NASA's James Webb Telescope is going to be optimized for infrared, and you can bet they're going to take a look at that star when it becomes ready. Why? Because it will be able to do such a better job than even Spitzer and look to see, are there any indications that there's an atmosphere, and if so, what's in that atmosphere? Okay? Give you one quick example, and then I'll finish with this question here. But if we found evidence of oxygen in an atmosphere, that could be a promising sign. Where does a lot of oxygen come from on Earth? Plant life. If you don't have any plant life, a planet will slowly, gradually lose its oxygen. Why? Because it reacts easily. It combines and joins with other elements, right? Things rust. So the point is, if you find a planet with oxygen in its atmosphere, you say, well, that seems pretty likely. There might be some plant life there. That could be interesting. Who knows? And if there's plant life, is there? We don't know that. Okay, so it's an exciting time. There's a lot of exciting questions. A lot of times people get going a little too quickly. That's fine, that's great, but just a little caution is in order sometimes. TRAPPIST-1, it's all over the news recently if you look it up. Spitzer played a big part in getting us a lot of the data there. My good friend Claire said I didn't read the first one.
I didn't hear you saying
The planets are what we call tidally locked. Maybe I did overlook that. So what does that mean? So, I don't know, would you like to be a star, sir? I mean, you're, okay, you be a star, I'll be a planet. And you're a pretty cool star, so if I want to stay warm enough, I better be really close to you, right? Well, it turns out if I'm really close to you, your gravity is significant. And to make a long story short, you're going to eventually affect me in such a way that only one side of me is going to face you. Think of our moon. We only see one side of the moon, don't we? Because over millions of years, the Earth's gravity has locked it in such a way that we only see one side. So, same thing. These planets are almost certainly tidally locked to their star. In other words, they're not spinning quickly like Earth. They're spinning just the right so that they always face the star. You say, okay, that's great. So what? One side is hot, one side's cold. And I mean very hot and very cold. So here's, again, as I said, another factor, right? Yeah. Here's another factor. If there's no atmosphere, you say, well, there's probably not life there, right? But wait a minute. If there's an atmosphere, maybe can the heat and cold kind of, mix? Yeah. How do you mix heat and cold in a planet's atmosphere? Somebody said it, yeah, wind. Well, the greater what we would call a temperature gradient or difference or change, the stronger the winds. So you're talking really, really, really strong winds. Okay? So again, we don't know a lot of the details here, but what we do know is that there's a lot of factors to be considered before you can kind of really say, hey, there might be life there. So I just wanted to share with you some of the latest updates here on TRAPPIST from Spitzer. Any other questions? So the question was about the upcoming solar eclipse, August 20th, 2017. If you can possibly get yourself to the place where the eclipse is total, you should do that. This is a big deal. It's super exciting. It's very dramatic. It's a very rare event. I am leading a trip down to Carbondale. I still have rooms, and they're not $500 a night, okay? So you're welcome to see me. I'm not making a pitch. I'm just telling you, if you can't get to Carbondale, there's other places you could go. Pretty much a lot of places across the United States, but there's a very narrow path where the moon will fully block the sun. The path of totality. There's many places, Kentucky, Nebraska, Wyoming, you know. So if you'd like to see me, you know, you're welcome to do that. Otherwise, try to get there. If you can't get there, I'll leave one of the other professors here to show you the partial view. No, you would see the moon partially block the sun. It's not really as exciting, but it's kind of interesting. I'm sure it'll be all over the news. I know it'll be all over the internet. But if you want to see it for yourself, I probably will have a professor with at least one telescope here on that. It's a Monday midday, if you want to swing by.
Monday morning.
Yeah, right. So that's kind of the short version of the solar eclipse 2017. Was there another question? Oh, okay, good question. How do they point Spitzer? Use it a little more of the... It's a pretty complex device. Boy, so is this microphone. Sorry. So different spacecraft use different ways of pointing and aiming. Yeah, some are a little simpler where they literally have little kind of jets where they shoot the jet and it kind of turns it this way. Problem there is, of course, you're eventually going to run out of fuel. Other telescopes have little reaction wheels where you spin a reaction wheel and it exerts a slight torque on the spacecraft and then it can move it. There's different ways to do that. I don't recall the exact details, honestly, on Spitzer. I'll go back and look for that. But I know it's not run out of reaction fuel yet. It's got a little bit left. It's not a super large, complex one, I don't think, with the reaction wheels. I'd have to look into the details for you. You can probably find it on the website if you really want to see the details of that. So where would you put an infrared telescope to be ideal? In other words, is a million miles far enough? Yeah, a million miles is pretty much far enough. And if you got that sunshade blocking the sun, you're pretty good. Ultimately, I guess you could put one outside the solar system would be even better, but that's a little bit impractical, more expensive, all that. NASA, way back in the early 1980s, had a kind of a first infrared telescope. They learned a lot with that, infrared astronomy telescope, and they incorporated that in the Spitzer. So it was, a certain compromise always of budget, capability, location, that kind of thing. So it was a very good location. Ultimately, I guess you could put one outside, yeah. So the question was, you've heard of large voids in space, and what I think you're describing are extremely large voids. There are certainly areas, even within our Milky Way, where there's this area, this area, this area, but when you use the word void, we generally use that to mean between galaxies. Does that sound familiar?
It's very large, dark
Yeah,
space.
enormous voids.
Unusually dark.
Yeah.
Unusually large and dark space.
Yeah, so essentially, when we look, and this gets into what we call cosmology, but essentially, when we look out into space, large distance, we don't see galaxies just randomly, uniformly spread. I don't know how well you can see that. But they're not randomly, uniformly spread apart. Instead, they clump together. You get stuff like this. Okay? Galaxies tend to clump together. And it's a long story, but to make it very simple, their gravity likes to tend to clump them together. Okay. What that means is you have large areas where there's no galaxies, right? You say, wow, that's a really big void. Does that sound kind of what you're asking about?
Right.
So what we talked about tonight plays into this question of, so what are these voids about? Did we just not get a powerful enough telescope, or is there? We really think they're empty, and here's why.
We believe they're empty or not.
Yeah, no, we really think they're really pretty empty. There might be a stray galaxy here or there, but they're pretty empty, and here's why. Because once again, our telescope technology is pretty capable these days. We would see, galaxies if there was a pretty good-sized galaxy in there. And the point is this: we can now again look at all these wavelengths. So in other words, there was something out there that was very cold, doesn't give off much light. We'd still see it in infrared with a Spitzer. It can't hide from us. If there was something very small but hotter, I'm just making another example, we'd see it with a ultraviolet telescope or an X-ray telescope. If there was this type of matter, we'd see it because it must give off this type of light or that type of light. In other words, most objects are betrayed by some type of light they give off. The exception to that is something called dark matter. Maybe a lot of you heard dark matter. Well, dark matter doesn't really give off light. So you'll never be able to look out here and see the dark matter. Well, how do you know it's there? All we know is because of its gravity. If there's a lot of dark matter here, it doesn't give off much light, it's going to pull on these galaxies and pull them towards it. And you say, why are those galaxies moving? Oh, there must be some dark matter pulling it or something. The question was, have we not figured out how to look at it or see it or find it or identify it or measure it? And the answer is, for dark matter, no, we can't see it. So that's true. We can't see it yet. Maybe someday we will. Right now, no, we can't. We can find what's called baryonic matter, which is, protons and neutrons and that kind of stuff like that, normal stuff that you and I are made out of. We could see that stuff. Even if it's cold, or even if it's hot, or even if it's big, or even if it's small, we'd see it. Normal matter, that we'd see. Those voids are empty of normal matter. I mean, there's very little, but this dark matter, that's kind of a whole separate question, okay? So there has been interest. Some of you know, been talking about a planetarium here at the College of DuPage. We have not been able to present to the board yet. Yeah, we have done some development work in terms of putting together a proposal. We will probably share that with the administration first, get more inputs, those kind of things. We've not been able to proceed with that yet. So the question was, the solar eclipse is the first day of classes at the College of DuPage. Where will I be?
Sick day.
Well, what I plan to tell my students is class will be in Carbondale, but it will be optional. If you really can't make it, I won't take attendance. But class will be in Carbondale that day. Classes will resume on Tuesday. That's the best answer I could give. I actually gave that answer to the vice president some months back, and he looked at me like, I said, that's what astronomers do. We go where we need to go. So, okay, so the question was, during our presentation, many times I mentioned, the dust is in a disk, whether it's around a star or even around a galaxy. And there's a very good fundamental reason why that is. It has to do with gravity and has to do with a few other physical laws. Picture a large, what we think early in the universe, you'd have some areas of the universe that had a little bit higher density here, a little bit higher there, a little bit lower there. And at some point, gravity would tend to make them roughly, and I mean roughly, spherical. Okay, so gravity, of course, is going to take this region and slowly the particles are going to kind of pull on each other. It's going to start to move towards each other, don't you think? Well, as they do that, of course, they get a little closer. You might know the closer they get, the stronger their gravity becomes. They go a little faster, a little faster. So as they're moving towards it, they're going a little faster. But now picture that the overwhelming majority of these particles are going to have some various particular motion. And they're not all going to perfectly head right to the center. They're going to be slightly off-center this way or this way. The point is this, sooner or later, that cloud is going to find the term we use sometimes is a preferred axis of rotation. In other words, sooner or later, it's going to slowly begin to kind of spin like this. Okay, this is due to something called angular momentum. And the smaller it gets, the faster it will spin. Think of an ice skater. Do you ever see these ice skaters in the Olympics? They go barreling down the ice. They go into their spin, right, and they do this. What happens when they pull their arms in? Turn into a blur. They don't do that. Why? Because of angular momentum. So my point is all this. Many, many, many objects in the universe, as gravity does its thing, they spin. Okay, great. Well, as they spin, they're still contracting downward, right, from most directions. But picture now this cloud. The particles up here are free to fall inwardly towards the center because they're not really spinning very much, are they? I think if you stood at the Earth's North Pole, you wouldn't really spin a very large distance, would you? You wouldn't have a very high speed or velocity. But in this roughly spherical cloud, the particles out here near the equator, as they're trying to collapse inwardly, but they're being spun, what do they feel? Sometimes it's called centrifugal force. In other words, they feel an outward force that prevents them from coming inward. So at the top and the bottom, they tend to fall inward, but in this direction, they tend not to fall inward, and you get a flattened disk. Does that help a little bit? I have all kinds of slides if you want to stay all night. We could look at them. Angular momentum, yeah. And so it's a very common phenomenon. That's why stars spin. That's why planets spin. That's why solar systems spin. That's why galaxies spin. That's why it's a fundamental physical law of nature. That is, gravity contracts objects, they spin faster, and as they spin faster, they flatten. It's like my room. No. So the question was, boy, we're putting a lot of stuff in space, telescopes and satellites and all that. Everybody wants to always have their GPS, right? Yes, there's a lot of stuff in space. Is there a lot of clutter? Yes. Is it a problem? Yes. Is it getting worse? Yes. Next question? No. So all this stuff is tracked, and from time to time it can be a problem. They can track a piece. There have been a few cases where even, for example, the space station, they say, hey, you guys need to go hide, just in case. It's a very low possibility. They've never taken much of a big hit, but sooner or later it could be a problem, not only for humans in space, but for other satellites. And one of the big concerns, of course, is if, let's say, somehow or other you did get a particle smash into a satellite enough to break it apart, well, now you got more parts. And now these parts go out and they smash into something else, and it could be like a snowball effect. You ever see Gravity, the movie Gravity? So anyway, your question is yes. There's a lot of stuff. It's a concern. Yes. We need to do a better job of cleaning up after ourselves, don't we? I hope you saw that Spitzer, obviously, again, is a very powerful tool, effective tool, a unique tool. It just opens a whole kind of new way of looking at the universe. And we could do something similar probably with other telescopes. There's ultraviolet telescopes. There's X-ray. You're going to want me to write a new presentation, aren't you? Great. But no, really, when you think about all these different wavelengths. And so again, these days, if an astronomer wants to study this object, well, a lot of times they'll study it at many wavelengths. Let's take an infrared picture. Let's take a visible picture. Let's take an X-ray picture. Oh, now we can put it all together and learn more about it. So that's very, very true. All right, well, again, great to have you all tonight. Thank you so much.